Hi guys, welcome to the first video presentation on time domain response. We've got two types of responses: frequency domain FD and time domain TD. As usual, engineer Motion Marfu is my name. For any communication with me, motionmarfu60@gmail.com is my email address, or you can come via WhatsApp +2637175358666. Guys, this is an interesting topic and I hope you are going to enjoy it. Let us go. Time response analysis, and we are saying in most control systems the independent variable is time, and control systems are inherently time domain systems. The response analysis of control system has become an important factor in the design and analysis of control systems. What do you mean by response analysis? It means the start of output behavior of a system as a function of time when it is subjected to a known input. And because we are doing it as a function of time, we are studying the output of a system as a function of time, we talk of time response. When we are studying the output of a system as a function of frequency, we talk of frequency response analysis, which is our next topic after time response analysis. Output behavior with respect to time, it must be within the specific limits to obtain satisfactory performance. And time response analysis of control systems helps us to evaluate the stability. We looked at stability and accuracy of the system. So in most control systems, the complete or final evaluation of the performance of a system is based on time response analysis and the corresponding results. This is self-explanatory. What do you mean by time response analysis of a control system? This is the output of the control system as a function of time when it is subjected to a known input, or you can define it as a response given by a system which is a function of time to an applied excitation. Excitation is our input because it excites our control system. It can also be defined as the analysis of response, or the analysis of response means to see the variation of output as a function of time or with respect to time. So this is how we define time response analysis of a control system. We'll be talking about frequency response analysis, which is analyzing the output of a system as a function of frequency when it is subjected to a known input. The response or the time response of a system to a known excitation can be divided into two responses: transient response and steady state response. And let us look at parts of time response. We are saying what we mean by total response, because we know that total response is equal to transient response plus steady state response. This is the response of a system from the time of application of an input to the point when time approaches infinity. Please take note, our t must approach infinity, and when t approaches infinity, we must also approach the steady state. So we are saying the total response consists of two parts: the transient response and the steady state response. And let's start analyzing what we mean by transient response. This is the response of a system from the time of application of the excitation signal to the time when the output has reached its steady state, and normally it is denoted by y subscript t of t. So mathematically can be stated as the limit of yt of t as our t approaches infinity, and it must be equal to 0, which means when t approaches infinity, the transient response must have died down, so which means it must be 0. What is the significance of the transient response? We get the following information. A, the time interval after which the system responds, taking the instant of application of excitation as a reference. So we can get time interval after which the system responds after applying an input. Is it taking too long to respond, or is it responding as soon as we apply the input signal? B, total time that it takes to achieve the output for the first time. We can get this kind of information from the transient response. Don't worry, it will be easy when we look at the diagrammatic illustration of transient and steady state response. We can also find out whether or not the output shoots beyond the desired value and by what margin or by how much. For whether or not the output oscillates, guys, you know the output of an oscillator has got a constant amplitude and constant frequency. So we can find out whether or not the output oscillates around its final value. Then last but not least, we can also find out the time that it takes for the output value to settle down to the final value. So a part of the time response of the system that goes to zero as t becomes very large or as t approaches infinity is known as the transient response, and it is obtained before the system reaches its steady state. So we saw that limit of y of t, which is the transient response, as our t becomes very very large or as it approaches infinity, is equal to zero, meaning the transient state dies down when t approaches infinity. The significant features of transient response of a system are: number one, the transient response helps in understanding the nature of variation of a system, how the output varies as a function of time. It does not follow the standard input signal light. Why does the output not follow the standard input applied? This is because there is inertia, there is friction, and also because of some energy storage elements like capacitors and inductors. It exhibits some damped oscillations. This means that the oscillations are stopped, they are damped. You will see that when we look at the response. Then the deviation between the applied standard signal and the output is high, but not desirable, and it has to be controlled before the steady state is reached. We always want the output to follow the input or to be equal to the input, but this is not always the case, as they need to control that before we reach the steady state. Then the other type of response is called steady state response, and this happens after the transient response, and we are saying the total response is equal to the transient response plus steady state response. This T stands for transient. Some authors put TR standing for transient, and this SS stands for steady state. So we are saying the steady state response is the system response after the transients have died and when our output is settled. So we are saying the time response after the transient response is called the steady state response. Or you can define it saying this is the part of total response which remains after the transient response has died out, and it is denoted by Y subscript SS. Its other name is forced response. So as I said, total response is equal to transient response plus steady state response. So we are saying all control systems exhibit transient behavior to some extent before they attain steady state. And we also saw that this is due to energy storage elements that are always part of the control system and they cannot be avoided. Due to these storage elements, the inductors, the capacitance, the response of the control system cannot follow sudden changes in the input instantaneously, and transient are observed. So we are saying as the input reaches its positive peak, the output might not reach the positive peak at the same instant or instantaneously. Thus, transient analysis is important as it plays a significant role in the dynamic behavior. This is the information that we get from steady state response. Number one, the time that output takes to reach the steady state value. Number two, whether or not an error exists between the desired value and the actual output value. Whether this error is constant, zero, or is infinite. You will see this is very, very simple. The total response, we saw that it is equal to time response plus steady state response. response. So we are saying the part of the time response of the system that is obtained as independent variable t approaches infinity is called the steady state response of the control system. We also saw that it can be defined as a part of the total response found after the transient response has died down. And what are its significant features? It helps, steady state response helps in giving an idea about the system of about the accuracy of the control system. Also, its feature is the independent variable t approaches infinity. The deviation between the input and output gives the steady state error. So we'll be dwelling much on steady state error in slides ahead. The number 3, steady state response of the system follows the transient response of the system. This we saw that after applying an input, we have got a transient response first, then as t is becoming very, very large, we approach the steady state response. Then 4, pattern of the steady response of the system varies like sine wave or like a ramp function. The graphical illustration of transient response, this up to there. This is the transient response, then the steady state response is from there to there. 0.98 is our actual output. The desired output is 1. So the difference between the desired output and the actual output is what is called the error. So this is an illustration of, so we are saying the total response plus the the total response is equal to the transient response plus steady state response. Steady state error and error constants. We are saying the steady state error is the difference between the input or our desired value and the output or the actual output of a closed system for a non-input as the response approaches infinite. That's the definition of steady state error. It also has got a mathematical definition. We are saying it is an important aspect of system behavior by which we measure the system accuracy. Another definition is the difference between the input value, which is the desired value, and the output, which is the actual response of the control system. And we are saying for a step excitation, the difference between the desired output and the final value of any system is termed as steady state error of the system, and it is given by steady state error ESS is equal to the limit of ET as t approaches infinity. If we take the Laplace transform, this becomes S and this becomes SE of S. So is the limit of SE of S as the S parameter approaches 0. Please take note of this. This is the Laplace transform of E of t. The Laplace transform of t is S. Guys, this is an important graph and it looks at time response specifications, and we are going to define these specifications. We are saying after applying the excitation at the input terminals of a system, an output response C of t is produced at the output terminals. Because we are analyzing time response, hence the use of these time response terms, which varies with the time as shown below. This is our time and this is the amplitude. So we are saying we've got what we call TR, rise time, TP, time delay, peak, the settling time, etc., etc. So we are going to define this. Also, not defining alone, given such a diagram, you must be able to label and also to define these specifications. What is delay time? This is the time that the output takes to reach 50% of its final value. That's delay time. And from our expression, this is our 50%, 0.5, and the time taken to reach the 50% of the final value is our TD. What is rise time? The time that the response takes to rise from 10% to 90% of the final value of the output is rise time. From 10% to 90% rise time. This is our rise time. This is our rise time, TR. The settling time. The time taken by the system response to settle down and stay within the plus 2% or this is 5% or to plus or minus 5 of its final value is known as the settling time, and this is our settling time. To 2%, this is our 2%. It can be plus or minus 5% of its final value. What is peak time, TP? The time taken by the system response to reach its first maximum value or peak value is known as peak time. The first maximum value of this system is Hence, this is the time it takes from 0 to reach this is what we call the peak time up to the first maximum value. Then steady state error, for a step excitation, the difference between the desired output and the final value of any system is known as the steady state error of the system. We saw that it is equal to the limit of the error as our t approaches infinity, which is the same as the limit after finding the Laplace transform of s multiplied by e of s as our s approaches infinity. Steady state response indicates the final output of the system, and by so doing it points towards the accuracy of the system. So we are saying in general, if the steady state response does not agree with the desired response exactly, the system is said to be in steady state error. Difference between the desired output, which is this, and the actual output, which is this, is called state error, and we saw that it is denoted by ESS. This is the steady state response, the transient response. This plus this gives us our output. So we are saying this is our desired output. The output got is this. The difference between the two gives us the steady state error. And we are saying we have got an input which is a pulse, and this is the way how the output varies when the input is a square wave. Hence we can see that this is our transient state and this is our steady state, and on our steady state we can see that the desired output and the actual output are the same. This is a revision of what we covered, and step input. This is the definition of a step input with amplitude A. So R of t is equal to A when t is greater than or equal to 0, or else it is equal to 0. And we are saying A is a real constant. We must be able to define this mathematically and also graphically. Standard step input. A step input is a standard step input signal whose value changes from one position to another position in 0 time. It is a function of time which is a 0 value for t, which is a 0 value for t less than 0, and has got a constant value for t greater than or equal to 0. The significance of this is that it represents an instantaneous change in the reference input. For example, when you turn on the switch light. This is the graphical illustration of a step input. It jumps from 0 to A in no time, and it remains constant, and its amplitude is equal to A. And when A is equal to 1, it is called a unit step signal, and this is the graphical illustration. Guys, you must be able to find its Laplace transform, and it is equal to A over S. Significance of a step signal: it represents an instantaneous change in the reference input signal of the system. For example, if the input is an angular position of a mechanical shaft, a step input represents the sudden rotation of the shaft. It is also useful in revealing the quickness of the system when an abrupt change is applied to the input, the way how the system responds to an abrupt change in the input. Please take note of the following. It is also known as the position input. All these standard signals have got alternative names, and you must be aware of them. Another standard test input signal, a ramp input. This is a ramp input. This is the standard input signal which changes linearly, as we can see, with time. It is also known as the velocity input. Please take note. Remember, the velocity time graphs at your O level. Mathematically, R of t is equal to AT, where A is the amplitude or the slope in this case for a rough input, and for t greater than or equal to 0, but for t less than or equal to 0, it is equal to 0. And we are saying its Laplace transform is equal to, for this, is A over S squared. If A is equal to 1, it is known as a unit ramp signal. The derivation of the Laplace transform, you use integration by parts, and you must arrive to x of s, which is the Laplace transform of x of t, is equal to A divided by S squared. What is the significance of a ramp signal? We know that it starts from t equals to 0 and varies linearly with time. It helps in testing the response of the system when a ramp signal is applied to it. For example, if the input variable represents the angular displacement of the shaft, just as we have concluded on step response, the ramp input denotes the constant speed rotation of the shaft. We know this is a parabolic signal, and we are saying what is a parabolic signal? This is a signal in which the instantaneous signal value varies with the square of time from an initial value of 0 at t equals to 0. It is also known as the acceleration input. You can see the rate of change is changing, hence the term acceleration. And we are saying its Laplace transform is equal to r of h is equals to a. This is of at squared over 2. It is a divided by S3, and this is the mathematical definition of a parabolic signal. Then the final standard test input signal that we are going to discuss is the impulse response for an amplitude of a, r of t is equals to 8t for t is equals to 0, and it is equals to 0 for t not equal to 0. And this is the graphical illustration. Its Laplace transform is equal to 1. That table is a summary of the standard test input signals, the type of input, the mathematical definition, and the Laplace transform. Guys, you must be able to do the derivative Laplace transform of this, not only to write the Laplace transform, you must also be able to define mathematically these signals and also to define using some graphical illustration. Let's look at another side of transient response, and we are saying systems behave differently just as humans do. Some people respond quickly to changing information while others take much longer to react. And also some people are more extrovert and quickly become overexcited while others take any change to their life in their stride. If we inject different input signals to systems, we also see that the system behaves changes. Some systems respond quickly, others respond more slowly, some become overexcited and bounce around, while others sluggishly follow the input signals. Human beings also behave the same. Some slowly, some overexcited, and they also bounce around. Remember what you can do if you are given the gift which you love most. While others, they sluggishly follow the input signals. What determines this behavior is referred to as the dynamic of the system, and although the dynamics of many systems are quite complex, we can often approximate complicated system dynamics by simpler representations. In spite of the enormous variation in transfer functions and physical natures of control systems, the transient response falls off of we've got 6 categories of transient response. Output responses from 6 different systems are shown here, and because the overall response is also depend upon the input function, it is assumed that every system is subjected to a step input. We will be analyzing the responses of control systems to step input, to parabolic input, to impulse, etc., etc. But for this analysis of the different types of responses, we are assuming a step input. In spite of the enormous variation in transfer functions and physical natures of control systems, the transient response falls off of we've got 6 categories of transient response. Output responses from 6 different systems are shown here, and because the overall response is also depend upon the input function, it is assumed that every system is subjected to a step input. We will be analyzing the responses of control systems to step input, to parabolic input, to impulse, etc., etc. But for this analysis of the different types of responses, we are assuming a step input. The first term of response that we are going to look at is called overdamped response, and how, if you are given a graph or a response in graphical form like this, how can you tell whether it is really underdamped, or critically damped? In overdamped response, as the system subjected to step input, the output slowly rises. As you can see, it is slowly rising. It's not a sudden rise, and reaches this final or steady state value after a long period of time. There are no oscillations as as you can see, there's no overshoot and undershoot, and the output never overshoots the final value, and it is normally found in milling machine when a small amount of overshoot results in too shattering or gorging of the material, ruining the surface finish. It is typical of a control system and used in machine tools, in printers, in plotters, etc. So this is the typical response with the time of overdamped response. Critically damped response is almost identical to overdamped response, but with one subtle difference: the time needed to reach the final value. It takes less time to reach the final value when compared to time needed to reach the final value is shorter. It takes time to reach this final value or for the output to be equal to the input. There is no oscillation or even overshoot. It is highly desirable in applications, in a number of applications, but it's difficult to achieve in practice. Can be designed and tuned for critically damped behavior, but there is possibility that with the passage of time we can have some system parameters changing. So as a result, a system which initially operated as critically damped may to underdamped. The characteristics of underdamped response is we've got overshoot and undershoot, and we've got some damped oscillations. These are damped oscillations, they will eventually die out, and also we've got fast rise time, overshoot, undershoot, and continued oscillations before the output settles down to this final value. This type of response results in the shortest time to first reach its target value. It takes time to reach its target value, but the amount of time taken to settle down may be much longer. As you are seeing, it is taking longer to settle down to this constant value or to a value that is equal to the input value. This is perhaps the most popular type of response, especially in the process industry, and the amount of maximum overshoot that occurs at the first peak of oscillation and the settling time are some of the criteria that are used for system design and controller tuning. We've got also what we call the constant oscillations. These are what we call the oscillations. I think you can see that the output seems to have constant frequency and constant amplitude, which is typical of the output of an oscillator that we studied in our electronic course. So we're saying the input is a step input, the output quickly rises, as you can see, to a value, but it will oscillate before it reaches its final value. Or in other words, it continues to oscillate back and forth about its final value, and it does not settle down even to its final value, as you can see. And this is more or less a hypothetical behavior because most of the physical systems contain some amount of damping to cause these oscillations to eventually die down. So there is no attainment of the final value. Then for increased oscillations, as you can see, there is some oscillation which is changed around the final value, but the oscillations are increasing in amplitude, as you can see, although the frequency is the same. And we are saying the output continues to increase in amplitude with each successive cycle, and eventually the system has to be brought to a halt, either through failure of the physical system through the constant increase in the amplitude or through some catastrophic event. And this type of response is highly undesirable. But for this exponential rise, as you can see, there is an exponential rise in the output for a constant step input, and we are saying it is the most severe type of system response whereby the output will continue to increase in an exponential manner without ever reaching its final value, and the system is normally brought to a halt either through failure of the actual physical system or through some catastrophic events, for example some chemical explosions or thermonuclear operations fall in this category. This type of response, as you can see, it is undesirable. Order and type of response. For a given control system, you must be able to state the order and also the type of response, and this is very easy. But first things first, this is the open loop transfer function, or LTF, and we are saying the denominator 1 plus gs is known as the characteristic function, and when it is set to 0, it is known as the characteristic equation, like in this case. And it is here that the poles of the transfer function are decided. We are saying the degree of the characteristic equation decides the order of the control system, and it is equal to the highest power of s. Don't worry. The highest power of S present in the characteristic equation of a closed loop transfer function of a linear control system is known as the order of a system. So given a characteristic equation, must be able to state the order of that particular system. So we are saying the open loop transfer function is obtained by breaking the feedback path or loop at the summing point. That is, we know that the open loop transfer function is equal to G of S plus H of S. There is no 1 plus. Please take note, it is not the same as this. This is closed loop. This is open loop transfer function or LTF. The number of poles of the open loop transfer function determines the type of the system. Take note, the number of poles of the open loop transfer function determines the type of the open system, and it is denoted by N, where N is the number of poles at the origin and type of system is N. We have got an open loop transfer function that is normally expressed as, guys, take note that this TA, TB can be on the denominator and T1, T2 can be on the numerator. It doesn't change anything. What we are saying is, take note of this, we've got our K there. We are saying this is known as a time constant form where K is a time constant. It is no longer the gain. And N, this N is the number of poles at the origin. Please take note. The value of N in the denominator polynomial decides the type of system. I said must be able to tell the order of the control system and the type of the control system. And we are saying if the power of S, if this power of S is 0, it is called type 0 system. If it is 1, it is called type 1 system. And if it is 2, it is called a type 2 system. Type of a system is the number of poles at the origin or the number of integrators in the system. Thus, order is loop transfer function. For example, we've got G of S, H of S is equals to this multiplied by this. This simplified is going to give us this there, right? If we equate this to this expression there, let's check what our N is. Our N is 2. So we can simply say there are 2 poles at the origin. That is from X squared. Hence, I boldened this 2. And we are saying, so in terms of the type of a system, the type of system is type 2 system from the power of S. So we are saying, how are we going to calculate the order of the system? We are going to, order refers to the closed loop function, hence this is our closed loop function. And check, guys, if you simplify it, you must get this. So we are saying our characteristic equation is equal to 0 after setting this to 0. And we are saying the highest power of the characteristic equation is 5. So we can safely say order of the system is 5. So is analysis of state error. We've got a closed loop control system we are familiar with. Input, reference input RS, which is the Laplace transform of R of t, the feedback signal of B of S, the error signal of E of S, the gain G of S, the feedback parameter H of S, and the output C of S. Want to analyze, and we are repeating. No need to define these. We know what they mean. B is the Laplace transform of the feedback signal. E of S is the Laplace transform of the error signal. R of S is the Laplace transform of applied input. C of S is the Laplace transform of the output. E of S, take note of this, minus is R of S minus B of S, but we know that B of S is equal to C of S times H of S, so we are going to substitute B of S in this, and it is going to be this. But we know that C of S is equal to G of S times E of S is equal to this, so we are going to substitute C of S in this equation. So it's going to be R of S minus G of S, E of S times H of S. Let us proceed. E of S is equal to this. We are going to arrange like terms together. This is going to cross the equal sign, and it is going to be equal to R of S. We are going to factor out E of S in this term. It is going to be equal to E of S in brackets 1 plus G of S, H of S. We are right. We are going to make E of S the subject of the formula. So E of S is equals to R of S divided 1 plus G of S, H of S as this. And please take note that for unit positive feedback or unit negative feedback, H of S is equal to 1. Hence, the denominator term will be 1 minus G of S. Even for unit negative feedback, it is going to be, the denominator is going to be 1 plus G of S, because there is no need of mentioning whether it is positive or negative feedback there. As long as it is unit feedback, this H of S is equal to 1, so it is going to disappear. So E of S is the error in Laplace transform domain. The corresponding error in time domain is E of t, mind you, it will be small letter, and t for time domain. And we are saying during steady state, t must approach infinity, and we saw that the steady state error is equal to E of S, which is equal to the limit of the error as t approaches infinity, and in time domain is the limit of S multiplied by E of S as S approaches infinity. And because this is equal to, so rephrasing, we can say we are now going to substitute this term S, E of S, in this term. So our steady state error is limit of S, R of S divided by 1 plus G of S, H of S as S approaches infinity. R of S divided by 1 plus G of S, H of S is this expression there. And this S is this of S, because this is coming from the Laplace transform of this. Please take note. So this is a formula for finding steady state error, is this formula in S domain. So we are saying steady state error depends on the following. We know it depends on R of S, we know it depends on U of S, H of S, and it also depends on dominant non-linearity. We are now going to analyze steady state error for different type of inputs. And we are starting, and encourage you to pay attention. We have derived steady state error for an open loop transfer function G of S, H of S, step input and steady state error. What this means is we are finding steady state error for step input. Then we also calculate steady state error for a ramp input before we start this steady state error for parabolic. So we are saying for a step input of amplitude A, R of t is equals to A multiplied by U of t, and the Laplace transform of S input at R is equals to 0 and having magnitude A is given by, this is the Laplace transform, and the steady state error, we know it is calculated from this equation. Please take note that our input, we are assuming it is a step input, and its Laplace transform is equals to A over S, as we have seen from this. So we are going to substitute R of S by A of S, and we are going to simplify there. It is going to remain A divided by this. And for a system with, we know that as S approaches 0, the limit of G of S, H of S as S approaches infinity is constant, and it is called the positional error constant Kp. This stands for position. So we are saying Kp is equal to this expression alone. So we can safely say steady state error is equal to, we have said Kp is equals to this expression, and so we are going to substitute this expression in this equation by Kp. So steady state error is equals to A divided by 1 plus positional error constant Kp. And we are saying for a unit positive feedback, we know that A is equals to, for a unit step input, rather A is equals to 1. Therefore steady state error is equals to 1 divided by 1 plus Kp. Please take note that Kp depends on the type of. For a reference input of R, this is the magnitude of R multiplied by unit step signal, R unit step signal. This is our reference input. Steady state input, we are going to have some damped oscillations, and this is our steady state error. Mind you, we are now in the steady state. So this is our error, and it is equals to, in this case, please take note that in this case, R divided by 1 plus Kp. Please take note. steady state error for a ramp input. The Laplace transform of a ramp input, which is equals to this, is 1 divided by s squared. But we know that steady state error is equal to this. So we are now going to replace RS by our ramp input, which is 1 divided by s squared. And if we simplify this, it's going to be the limit of a divided by s plus s g of s h of s, and as s approaches infinity, this is going to approach 0. So our steady state error is going to be a divided by this. And for a system, this is constant, and it is known as velocity error coefficient. Please take note that this is a ramp input, so it's velocity error coefficient, and it is denoted by kV. We are now going to replace this by kV. So our steady state error is equal to a divided by kV, and kV depends on the type of system. Please take note that if it is the step input, a is equal to 1, and for a unit positive feedback, hs is equal to 1. So E of SS is equal to 1 divided by AV. Please take note, this is important. This is important. We are deriving something, but this is important. This is our ramp input, the straight line, and this is the response to a ramp input. And please take note that it's now constant. The steady state error is now constant, and it is the difference between this input and this output. Please take note that you must be able to, given this curve, you must be able to identify the type of input, parabolic input, and steady state error. And we are going, this is our parabolic input. Its Laplace transform is equal to this, and we know that steady state error is given by this. We are now going to replace RS by our input, which is this, the Laplace transform of this, and we are going to simplify. If we simplify, the s and the s are going to cancel, but the s squared is going to remain. So this is our steady state error. But as s approaches 0, this is going to approach 0, and the simplified form is going to be this. And please take note that this is a constant, and it is known as acceleration coefficient, and it is noted by A for acceleration. So we are saying acceleration is equal to this expression, and as usual, it depends on the type of system. And for a unit ramp input, A is equals to 1. Therefore, for a unit ramp input, steady state error is 1 divided by K of A. And let's look at the response. This is the response for steady state error. We know this is our ramp input, and our output is going to undershoot like this until it settles, and the difference between this and this is shown by this, and we call this steady state error. Please take note, given this, you must be able to identify the input, the output. This is a sinusoidal signal, and its amplitude is A. This is the symbol. This is the mathematical definition of sinusoidal function. F of t is equals to A sine omega t plus theta, and A is the amplitude. Omega is angular frequency, and it is equal to 2 pi f. F is equals to frequency, and theta is phase. And it is also a standard input signal, and it is used for testing response of electrical networks, audio, video, and also for industrial control systems. And these are the standard test signals that are used for frequency response analysis. So we'll be looking at this when we do frequency response analysis in our next lecture or chapter. That is a summary of the static coefficients. These guys: positional error constant, Kp, velocity error constant, acceleration error constant. They are also known as static error coefficients. Please take note of the symbols: P for position, V velocity, A for acceleration. These are the equations for these three, and this is the formula for finding the steady state error. Please take note. Sometimes you are required to find these when the input is a step input, also this when the input is a ramp, and also when for a parabolic standard test. Steady state error for type 0, type 1, and type 2 systems. Nothing to be afraid of there. Before long, you'll be able to identify types of systems and also order of systems. So we have met this, the general form of an open loop transfer function. We said it can be given by this, and from this equation, n is the number of poles, and it identifies the type of system. So you must make sure that your equation is in this form when you are asked to find the type of system. And we are saying for type 0 system, our unit feedback system, the open loop transfer is given by this expression. Why? Because s to the power 0 is 1, hence there will be a 1 there. Hence this evaluates to this. The steady state error for unit feedback system, take note we are discussing it for unit feedback system. H of s is equals to 1, so the steady state error is equals to limit of s times r of s divided by 1 plus g of s as s approaches infinity. But for non-unit feedback system, h of s will be there, hence this will be our steady state error as we derived. We've got some questions there. Identify the type number. We've got g of h is equals to this, h of s is equals to this. So we are going to multiply the two and we are going to make sure that our equation is in this type. So it's now in this type there, and you can see that s is to the power 2, hence this is a type 2 system. So the index identifies the type of system. We've got another one, g of s is equals to k divided by s, h of s is equals to 1 divided by s plus 2. We are going to change it to standard form by multiplying the 2. Please take note that s is squared. This identifies our type of system. So this is a type 2 system. Another expression, we're going to multiply this past this. So this is going to be our expression. And please take note that this is a type 0 system. Error for a step input, this is the steady state error, and we evaluated it and we found that it is equal to a divided by 1 plus kp, positional error constant, where kp is equal to this. And for a type 0 system, then when in this case n is equal to 0, so s to the power 0 is equal to 1, hence this is the standard expression. And we are saying since kp is equal to this, therefore our kp we are going to substitute into this. This is equal to 1, 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 hence kp is equal to k times 1 times 1 divided by 1 times 1 times 1, which is equal to kp is equal to k, hence steady state error is equal to a divided by k in this case. And please take note that this graph is showing the error for step input type 0 system. Step input for a type 0 system. For a type 1 system, please take note that we're looking at type 1 system. Let's have a look at, we're having a look at type 0, and we said this is the response of type 0. Take note of the ESS. For a type 1, this is equals to s to the power 1. So in this case, n is equals to 1. So we are saying under such an expression, if s approaches 0, what this means is all our denominator is going to approach 0. If our denominator approaches 0, it means that this expression is going to evaluate to 0. Hence we are saying steady state error for a type 1 system is equals to a divided by 1 plus k, and our k is infinite in this case, so our steady state error is going to be 0. Hence if we have a look at our graphs, you can see that for this graph, this is a step input. Eventually the output will be equal to the input. Even in this case, the output, though it is taking time with these damped oscillations, it is eventually going to be equal to the output, to the input. Hence it's different from this. This is going to remain. This is steady state error is going to remain. This steady error is going to remain. But for a type 0 system value, for a type 1 system, from this evaluation, we can see that it is the steady state error is equal to 0 for a type 1. Even for a higher order systems, as long as we have got an S there will be no steady state error. In other words, the output will be equal to the input. But for a type 0 system, steady state error will be constant and will be equal to this. We saw that steady state error for a ramp input is equals to the limit of a divided by kv as s approaches infinity, and this is our kv. But for a type 0 system, n is equals to 0, hence this will be our equation. But we know that kv is equals to this. Please take note of this expression and see how it goes to 0, because we've got an s there on the numerator, so this goes to 0, which means our kv goes to 0. If we visit our equation, If this goes to 0, it means that the steady state error is equal to infinity, and this is the response. This is our input, the ramp input, but as you can see, our ESS is widening and widening, and it ends up approaching infinity. So we are saying for a type 0 system, this is the response of our system, and this is coming from this expression. Please take note. If you cannot appreciate this, then it's difficult to appreciate this, because this is coming from this expression. Infinity is coming from this derivation there, and this is coming from this expression, and this is our S. So this is going to approach 0, the denominator is going to approach 0, so the steady state error is going to approach infinity. Pay close attention for time response of a type 1 system whose input is a ramp input. So we are saying this is our open loop transfer function. Take note that our n is equals to 1, showing that this is a type 1 system, but we know that the error coefficient for ramp input is equals to limit of g of s, h of s as s approaches infinity, and take note that got an s there. So we are multiplying this by this, because this g of s, h of s is equal to this. So if we substitute this in our equation, we know that this expression there is equal to s g of s, h of s. So this s and this s, they cancel. So this will be our result explanation. And if s approaches 0, it means that this term is going to approach 0. The same applies to this, and same applies to tn multiplied by s. So the numerator will be k times 1 times 1 times 1 times 1. The denominator will be 1 times 1 times 1 times 1 times 1, because this s will cancel with this s. So our kv will be equal to k, which is a constant. So we are saying our ESS, steady state error, will be a divided by kv. So it will be constant as shown. So guys, take note, for a type 1 system, the steady state error, it will not approach infinite, but it will be a constant. Response for a ramp input for type 2 systems and above. This is our open loop transfer function. Take note, for type 2 it's s squared there, and we know that a ramp input kv is equals to this. So if we multiply this by this, is limit of s multiplied by this is equal to this. So we know this s and s in s squared cancel, so this s is going to remain, and if it approaches infinite, this whole denominator is going to approach 0, and the result of kv is equal to infinite. So this means that for any system that is of type 2 and above, the steady state error will be equal to infinity, as shown by this table there. For type 2 system or higher, steady state error is equal to 0. So you guys must be able to, you must know this, we must be able to deduce from this expression. So let's have a look at what happens to the steady state error. The steady state error, if kv is equals to 0, is going to be 0, and this comes from the formula. This is our formula. If this is infinite, then the steady state error is going to be 0 for ramp input and higher order systems. Error for a parabolic input. This is now our standard input, and it is the last one we are going to discuss. So we know that for a parabolic input, steady state error is equal to a divided by ka, where ka, steady state error for a parabolic input. This is the last standard input that we are going to discuss, and we know that for a parabolic input, it is given by a divided by ka, where ka is the constant error coefficient, and it is equals to limit of s squared multiplied by the open loop transfer function as our s approaches infinity, and for a type 0 it is stated as. So we know that this is equals to this, and if we substitute our original expression in square brackets in this equation, it is going to appear as this, and we know for type 4 s is equals to 0, the s there is 1, hence it's going to appear as, and if this approaches 0, the whole expression will approach 0. So our steady state error will approach infinity if our coefficient approach 0 as shown. So the type 0 system fails to keep track of a parabolic input due to increment of errors continuously. Let's analyze the response, the steady state error for a type 1 input. For our type 1 input, we know that s there is equal to 1, hence is s to the power 1, which is s, and we know that our ka is equal to this term. So this expression, there is an s there. If we simplify this s is going to remain, and which means that Ka is going to be 0 for a type 1 input. Hence the steady state error will be infinite. This is the response of the system for type 0 system, and you can see what is happening. Our steady state error or our parabolic input is approaching infinity. But for a type 1 system, guys, if you simplify this, you will see that your constant will be equal to K, and this is for a type 2 system, it will be equal to A over K, and for a type 3 system, it is going 0. So we cannot emphasize often that now for this result to be valid, closed loop system must be stable. Take note of the summary of this table. For a type 0, steady state error is close to infinite. For a type 1, infinite. For a type 2, constant. And for type 3 system or higher, it is going to be 0. This is constant, and this is for a type 2 system. You can try to sketch for a type 3 system or higher. There will be no errors. So as we can see, steady state errors can be reduced by increasing the value of K, but there are limitations from stability point of view. Practice questions. Find the error coefficients of a system having. Error coefficients are these: constant positional error constant, velocity error constants. It's called velocity error constant or velocity error coefficients, acceleration error coefficients. So you must know these formulas. We know this is for a step input, for a ramp input, and A for a parabolic input. And if you know this, there's no S there. So which means for this, if this approaches 0, it means that the positional error coefficient is going to approach infinity. For a velocity error coefficient, take note of this S there. This S and this S are going to cancel, so this is going to be our expression, and if this is 0, is the same as 3 divided by 1, which is close to 3, so this will be our velocity error coefficient. For our acceleration error coefficient, take note of this S squared there. One S is going to remain after the other S would have cancelled with this S, hence there is this S there. So what happens? If this approaches 0, it means that the numerator is going to be 0, so the acceleration error coefficient is going to be 0, and you are done. This is a typical exam question. Please take note. Find positional error coefficient, velocity error coefficient, acceleration error coefficient for the system having. Take note of the GSS and the H of S. We know that for a positional error coefficient, it is equal to limit of G of S, H of S as S approaches infinity, and we multiply the two, get limit of 7 divided by S squared as S approaches 0, and we know our Kp will approach infinite. What about our Kv? Our Kv is limit of S, G of S, H of S as S approaches infinity, and please take note of this S. G of S, H of S is 7 over S squared, so this S and the S squared are going to cancel, so it is going to remain limit of 7 over S as S approaches infinity. So also our velocity error coefficient is close to infinity. This is a typical exam question. For a acceleration error coefficient, take note it is equal to this, and this is a constant. If we multiply the two, we are going to have, this is going to simplify to 7S squared divided by S squared. This is the S squared, so it is going to be 7. Another example, G of S is close to this, H of S is close to this. We are going to multiply, we are going to find the error coefficients, and for positional error coefficient, we know it is Kp is close to this, so we simply insert this expression after multiplying these numerators. This is 3, and if our S approaches 0, this is going to be 3/5. For velocity error coefficient, take note of this S. Going to multiply this S by the product of G of S and H of S. So after multiplying the two, take note of the S. This S is this S, and if our S approaches 0, this is going to be 0. So our velocity error coefficient is going to be 0. Acceleration error coefficient, take note of the S squared. This is our S squared. It is also going to approach 0 because the numerator is going to be 0 if our S approaches or tends to 0. Right, in this time response analysis of control systems 1, we are going to end by discussing advantages and disadvantages of static error coefficient method. Static error coefficients are Ka, Kp, and Kv, and we are saying this method is applicable only to 3 standard input signals we discussed and cannot give error coefficients for other input signals. Please take note, mathematical response of errors that is 0 and infinity cannot give exact value of error, because it might be 0.5, 0. Or it might be a large number which is not an infinite number. This method can provide the important time variation of error, then it can be used for stable systems only. For unstable systems you cannot use it. Guys, this is the end of our lecture on time response analysis of control systems 1, and I hope you've enjoyed. You must be able to define the static error coefficients Ka, Kp, and Kv, and also must be able to determine, given an open loop transfer function, the type of the system and the order of the system, and also even to sketch the response for different types of inputs. The steady state error for step input, for ramp input, and also for a parabolic input. Guys, if you are learning something from the videos from Telecom Academy, don't hesitate to subscribe. You can even comment, or you can even like. So until then, let's meet in our time response analysis of control systems 2.